So I think when I first showed off an early version of these tutorials, the one area I got more questions about than anything else was this aiming line here, this line that showed you where your ball was going to go as soon as you shot it. And I guess this kind of surprised me because it's actually one part of the application that doesn't really use Box 2D. Of course, maybe that's why it got more questions than anything else, because it's one of the areas where we can't rely on Box 2D to do our physics calculations for us. I mean, the way I see it, there are probably two options to create a pretty good aim line. Option one, which is kind of the crazy one that I haven't actually tried, is to create a parallel world that is a duplicate of our current one. We could create a new B2 world object. We could populate it with all of the stuff that's in our current one, and then we could, outside of our normal enter frame listener, step through several time intervals in this parallel Box 2D world and see what happens to some theoretical ball that we launch through the world. And that could be a very, very accurate way of predicting what would happen with our ball when we launch it in the real application. Now, this is so crazy that I kind of want to try it just because I think it's really weird. But I kind of think for the purposes of a tutorial, it's a little too complicated. Plus, I have no idea if I could actually get this to work. I haven't tried it yet. So option two is to just kind of reproduce what Box 2D does. And it turns out this is easier than it might look at first if you ignore things like collision. If all I'm doing is reproducing the way an object moves with acceleration in one dimension, that's actually fairly easy. And this is essentially how we're going to do it. Let's say we've got a ball, and this ball has a certain velocity. Over some particular interval of time, maybe it would be 1 second, maybe it would be like 1/30th of a second, our ball is going to move a small interval, and that interval will depend on its velocity. Now, if we are in a world where there is acceleration, for example, due to gravity, we're going to take that velocity, add a little bit of the acceleration due to gravity, and we will end up with the new velocity that this ball is going to travel during our next time interval. And so the next time we update our ball, it's going to move slightly different than before. And again, we're going to take the ball's current velocity, add the acceleration of gravity. We end up with a new velocity, and we keep doing that for several steps. And we eventually get our ball traveling in an arc that is affected by gravity. So keep this in mind, because this is basically what we're going to do for our aiming line. So let's go back to our code here and start working on the aiming line class. I'm going to create a new class, and I'm going to call it aiming line. Now, the way I see this class working, it's going to be a sprite that is going to exist in our application, and probably at regular intervals when we're aiming, we're going to want it to show the path that the ball would travel when we are at a particular point, traveling in a particular direction with a particular velocity. So let's start building all of that. First things first, I think when I create this class, I'm going to pass to it the gravity in meters. This is something that we should have already in our main application, and we will need to know what the acceleration of gravity is, and we're going to need to keep track of that. Call it gravity in meters. It will be a number. All right. And then the function that we're probably going to call is going to be something like show line. We're going to pass to it the start point. We're going to pass to it, say, the direction. And we're going to pass to it the velocity in pixels, because I guess that's what we've defined it as in our main Puggle application. Now, I suppose I'm probably being somewhat confusing with my use of velocities. In some cases, I talk about velocity as a vector with, an x and y value. In this case, I'm talking about velocity as sort of the overall speed or the overall length of that vector. I'm sorry about this being somewhat confusing. I'll try and think of a more consistent way of naming things in the future. So that being said, actually, since we know the direction we're going to be traveling in and the length of the vector that we want to eventually produce, let's create our velocity vector. which will be a point. And for starters, we're going to take our direction and we'll clone it, get a copy of it. The vector that our ball will be traveling in pixels. Now the next thing we're going to want to do is normalize it. And this basically sets our vector, or I suppose our point, to be a particular length. And since we know what our length is going to be, that's our velocity in pixels, we can normalize it to that. So at this point, we have a velocity vector in the right direction and at the right length. And maybe we can specify this. And our length is going to be in pixels per second. That's what we've got right now. The next thing we probably want to do is figure out our gravity in pixels, which should be our gravity in meters multiplied by a ratio, just to make sure we've got everything in the same units. And then we can basically go through this gradual step process that you saw in the earlier diagram. So initially, I'm going to create this little step point, and it's going to equal essentially our start point. And I'm just going to clone it. And from here we can start drawing, actually. So I'm going to first clear our graphics. I will set the line style, and in this case I'll set a thickness of 12, since I happen to know this is actually the diameter of the ball sprite, and I think that will give us a more accurate aiming line. For a color, I don't know, let's take something like that, nice green. And for our alpha, let's go with something a little less than 1. We'll go with 0.4. And we will move to our step point x and our step point y. So at this point, we've got our pen at the location where we want to start drawing, and we know the velocity that we want to travel in terms of pixels per second. Now, if we were to step through the process of drawing this line, and each time we did it, we incremented our line by this velocity in pixels per second, it wouldn't be particularly well drawn. It would probably last 1 or 2 segments, and suddenly we'd be drawing off screen, because after 1 or 2 seconds, our ball has basically fallen off screen. So instead what I'm going to do is I'm going to draw the path our ball is going to travel in something that is less than 1 second. So what I'm going to do is I'm going to create a variable called, granularity. And let's make that, 20. And this is going to be basically the steps per second that we're going to draw. And so now what we can do is we can simulate 1 second's worth of our ball falling through our world. And we can do that basically by drawing these little mini steps. So let's do that. I guess first things first, I'll set up a little loop here. I'll have for var I int equals 0, I will be less than our granularity, and I plus plus. So basically, I'm going to draw 20 mini steps to simulate exactly 1 second's worth of our ball falling through our world. First thing I'm going to do is I'm going to apply gravity to our velocity vector. So we're going to take our velocity vector's dot y value, and I will add to that our gravity in pixels. And because our gravity in pixels right now is in pixels per second, and I want pixels per 20th of a second, I'm going to divide this number by our granularity. Now at this point, I can take the position of the ball and apply this velocity to it. So I'm going to take our step point dot x, and I'm going to add to that our velocity vector dot x. And again, I'm going to divide by granularity because our velocity is in pixels per second, and I want pixels per 20th of a second. And I'm going to do the same thing for step point y. And now that I know where a ball is supposed to be, I can just draw to it using the line2 command. You may be asking yourself, why did I apply gravity first and then apply the velocity to the step point? I actually have no real good answer for you, except that this way seemed to work better. So I tried it both ways. This way worked better. I should probably have a better answer for you prepared than that, but I don't. So to review, all we're really doing here is creating that diagram where we took a point, we knew our acceleration of gravity and our initial velocity, and through a series of little steps, we simulated the way that point is going to fall in space. And by doing that, we're able to pretty accurately predict where this ball is going to fall in our Peggle world. This won't be exact, probably depending on even things like your computer and, what chip you've got underneath the hood. You may end up with slightly different numbers than what Box 2D ends up with. However, I think probably for most intents and purposes, this will get you an aiming line that should be accurate enough to use in a game. So now, just to make sure this all works, let's jump back to our Puggle application. And I'm going to create a new variable called aiming line, which will be an aiming line. And then down here, I'm going to create our aiming line. It will equal a new aiming line. And we'll pass to it our gravity in meters, which right now is hard-coded at 9.8. I might fix this later. And remember that because it's a sprite, we need to add it to our display hierarchy. So I'm going to have our camera add our aiming line as a child. And then just to see if things work, maybe what I'll do is I'll have our aiming line show a line. We'll draw a point somewhere roughly in the middle of our screen. We'll have it shoot, roughly to the left and down a little bit. And we know that our launch velocity is this constant that we have above. By the way, at some point I changed this to 180. You might have a lower number, but that's what I did. So let's try this just to make sure it works. Well, it looks like we are clearly tracing the path of some object. I have no idea if this actually matches up with anything yet because we haven't built that functionality in, but we will do that in the next lesson.